Let's start with the second question from Bit Manipulation Power Set question series from Striver CP Sheet. The question says Theophanes really likes sequences of positive integers. Thus, his teacher gave him a problem about sequence that consists only special numbers. Let's call a positive number special if it can be written as sum of different non-negative powers of n. What it means? So this is a number 17. We can be write it as 4 raised to the power 0 plus 4 raised to the power 2. We can see that these exponents are different. We cannot write 4 raised to the power 0 plus 4 raised to the power 0. We cannot write it like that. So yeah, so this is how we are going to write it, and this base should be equals to n. So this is how are we defining the special numbers. So we need to find the kth special number if all of them are sorted in increasing order, and we need to output them modulo 1e9 plus 7. So this is what the input is. So so one observation that we have to make here is that the first number will be n raised to the power 0, which will be 1, right? Next will be this, this will be n, right? Next will be n raised to the power 0 plus n raised to the power 1. So, yeah, so this will be the third special number. Okay. Then we will have n square, right? Okay, so rather than taking n, let's just take some n, let's say n equals to 4 or k equals to some number, right? Let's start with this. We have this is the first number. Second number will be 4 is to the power 1. Third will be sum of both, right? We can take sum of both. Is there any number between 4 and sum of these? No, because sum of this is 5, right? There can be no number. What is the next number? Think of what can be the next number. Can we have 8? No, because 8 will be 4 to the power 1 plus 4 to the power 1. That is not allowed. We need unique powers. What will be the next number? Next number will be 4 square, which is 16. Right. What can be the next number? So can we add any of these to the 16? Yes. The fifth number can be, we can add this. Right, this is 17. So this is given in the question. What can be the next number? The next number will be 4 to the power 1. Right, this can be the next number. This will be 20. Can there be 18 or 19? 18 or 19 cannot be there, right? uh, you can check and verify. So what is the pattern? The first number is 0, the next is 1, the next is 0 1, like I'm just writing the exponents. The next is 2, the next is 0 2, the next is 1 2. Are you able to see a pattern? This is bit, like this, the set bits from 1 to n. Like 1 can be written as this, right? Like 0, this is 1, right? 0 1, this is 2. Then we have 0 0 1, the second bit is set, right? Yeah. Sorry, the next is not this. um, yeah, this is the second bit. This is 2. Then this is the third. 0 and 1 are set. This is 3. Then the second bit is set. This is 4. Then 0 and 2, which means 0 and 2. This is 5. So can we see the kth number? To find kth number, we'll have to we'll have to add n to the power I and summation of these, where I will be the set bit, all the set bits. For example, for the fifth number, n to the power 0 plus n to the power 2. So yeah, this is a very direct question. We just needed this intuition in this problem, and now we can directly implement this. So yeah, we take the input n and k, and we start with the fact equals to 1, or rather than fact, let me just write it as exponent, right? So what we are doing here is we are starting with the exponent 0, and we are checking which bit is set. So let's say we are starting with the 0th bit. If this is set, how will we check it? If this is set, this can be checked by performing the AND operation with k and 1. So let's say if the 0th bit is set, then we'll perform AND operation, and this will give us 1. Then we'll remove this, and then so the 0th bit is set, and then we come to the first bit, and yeah, this is also set, and then we remove this and we come to the second bit. This is not set, right? And similar thing what we are doing here, we are checking this operation, right? And if the bit is set, then we are adding n raised to the power exponent using this power mod function. This is a binary exponentiation function, normal power function. The difference is that we are doing the modulus operation here, right? You can learn about this. This is a topic of binary exponentiation, and yeah, and this is the power mod function. So we are adding it to the answer, and after each operation we are adding 1 to exponent because we are moving ahead in the bit indexes, and we are also removing the last the rightmost bit using this right shift operation, and finally we are printing the answer. This was a pretty straightforward question. uh, yeah,